So hello, everybody, and welcome. I have 105. So thank you for joining us. If you missed Tuesday's recording...
Hey, Robert, you're still muted.
Are you sure about that? He didn't seem muted to me.
Yeah, no, I'm definitely talking. Does anybody other than Ted hear me?
Does anybody not hear him?
Besides Mandy. Okay, so I think this is working. Can we? Can I get a thumbs up though from people if you hear me? Okay. All right. Excellent. Sounds good. Okay, so on the past, on Tuesday, we worked through the exercises from last class. They were looking at Hodgkin-Huxley and temperature change. This statement at the beginning was false. They in fact did examine the role of temperature, and NEURON does what they said to do. So it's all well and good. So in Tuesday's class, we looked at the parameter sweep. We saw some parameters that we can adjust with EFEL to adjust how it determines when an exponential starts and stops. In the process of this, I think we talked about how to make our cell classes a little bit better so they print out nicer. So that'll help with debugging and give us consistent displays sections whenever we restart. We also, when we looked at the morphologies, we built up some nice little tools that we can use on just any old SWC morphology to look at, for example, the minimum and maximum diameters, how the diameters vary over distance, and some code for checking out whether or not how current spreads within the cells. And in exercise 3, we actually simulated a cell with morphology starting from the SWC. And in the process of this, we also talked about the d lambda rule a little bit, which is a principled way of giving at least an initial guess as to what you think is an appropriate choice of discretization. So does anybody have any questions on any of that material, or did anybody approach things in a way that was significantly different that they'd like to share? Okay. Well, if not, that's excellent. If you haven't had a chance to check it out, please do, because I think there's a lot of useful material there. And I went through everything starting from the beginning, so you get to see how I approach the problems, sort of, so it's not like, here's the answer, but this is how we build up to the answer. And if there's no other questions on that, then today we're going to talk about networks. And so Ted's going to start it off, and then I'll come back with the parallelization part. So, Ted, you want to take it away?
Okay, let me see if I can successfully share my desktop. Okay, that's odd. Very peculiar. Hold on a second. Let me try this again.
I just made you a co-host also.
Okay, there we are. Portion of screen. Share. There we go. Okay, so we have here my first slide, which I'm assuming everybody can see.
Looks good.
Okay, so if you're going to be modeling networks, your first task is, of course, after you've come up with a hypothesis, which means you've decided what kinds of cells you need in your network, what sort of network architecture you're going to be using, what kind of synaptic mechanisms are going to be involved, and all that good stuff. I mean, all the interesting science part. Once that has been done, you have the task of actually instantiating the network. And to do that, you first are going to have to, well, you can do anything in any order that you want. And but if you're not careful, you could end up with spaghetti code. So a good way to think about it is to do things in an orderly fashion. First things first. Well, what comes first? Define the types of cells that are going to be in your network. You've already made up in your mind the decision as to what it is in the biology that you want to represent and how you want to represent these cells. Are they going to be full branched architecture from morphometric reconstructions? Are they going to be stylized ball and stick type cells? Are they going to be single compartment models? Or they could be something else? And we'll get to what something else it could be. But you have to define your cell classes that you're going to then use to spawn the instances of cells that you're going to use to build your network. Okay, the second task, of course, is creating those instances, right? And keeping track of them somehow, all right? Which usually means creating a bunch of them and appending them to lists. So you may have a list of all the pyramidal cells. You may have all the lists of CA1, all the CA1 pyramidal cells in hippocampus, for example, and all of the CA2 hippocampal pyramidal cells may be in a different list. Or you might just have one single list that contains all the different kinds of, all the instances of all cells in your network. However, it makes best sense to you to structure it. And your third task is to connect the cells. Well, we've already gone through some of what's involved in defining types of cells, and you've seen good patterns to use in Robert's presentations in Python for doing that. You also know you can export cell classes from the cell builder if you like, and you can reuse those with networks that are otherwise specified with Python and with cells that are otherwise specified with Python. We know about how to create cell instances, and the last question is, how do we go about connecting them? Okay. Well, let's think about the kind of communication that exists between cells in a network. I'm leaving out for the moment, well, for the duration of this particular presentation, I'm leaving out anything that involves the spread of neurotransmitter or ions throughout extracellular space, that is synaptic spillover or efflux of potassium from cells or depletion of extracellular calcium because of massive intracellular, massive calcium influx. Not that I think that ever happens particularly. And I'm also leaving out ephaptic interactions, that is, interactions that result as a consequence of the local electrical fields generated by one cell on the branches of other cells that are nearby. So we're going to focus on gap junctions just a little bit. Well, actually, we're not going to talk about gap junctions. We do have to think about them, and there are ways to deal with gap junctions, but they're basically similar to the way we would deal with synaptic transmission that's graded. And we'll get into that shortly. The other kind of communication is spike-triggered communication, that is, in which a postsynaptic cell doesn't know what's going on in the presynaptic cell until the presynaptic cell fires a spike, and that spike propagates down to the transmitter release zone in the presynaptic terminal. Okay, So let's take a look at synaptic transmission, skipping over gap junctions for the moment because it's the way we manage those is very similar to the way we deal with graded transmission. What's graded synaptic transmission? Well, in the retina, there are synapses which release transmitter all the time, and the rate at which they release transmitter is actually a function of presynaptic calcium concentration. Okay? But we can make a more abstract model, conceptual model of graded synaptic transmission in which the physical system consists of something that's presynaptic that has a variable that governs the continuous release of transmitter, and that the transmitter somehow gets across the synaptic gap to receptors on the postsynaptic cell where it then where the transmitter then interacting with the receptors modulates some postsynaptic property. Typically that postsynaptic property is a conductance of a ligand gated ion channel, the open or closed state of a cluster of such channels, but it could be some other thing entirely. It could be modulating, say, the reaction rate of a mechanism that produces intracellular second messengers, or it could modulate calcium, it could modulate something else, okay? So it doesn't have to necessarily affect synaptic conductance. But for this illustration, we'll keep it simple. So here we have a cartoon of our presynaptic terminal and our postsynaptic cell, and we're saying that there's a channel, an ion channel here, or better yet, a synapse, whose net synaptic conductance attached to this postsynaptic cell is some function of a presynaptic variable. And for the sake of simplicity, we'll say it's membrane potential, but we all know it's probably presynaptic calcium raised to the 4th power or something. Okay, but if you look at the way people have been implementing their models that use graded transmission, they often just use presynaptic membrane potential as the variable. So we have this conductance in the postsynaptic cell being a function of a voltage in the presynaptic cell. And immediately we have a problem. When you think about how you're building models, you realize that when you specify a cell as a bunch of sections connected to each other, what you get for free is you get communication, electrical communication between adjacent regions in that cell by way of the cable equation, okay? So every patch of membrane knows its local membrane potential, and every patch of membrane is generating a current which spreads laterally, longitudinally to other regions of the cell, and also axial currents can spread into the region where our patch of membrane is located. So we get all that stuff for free. But it all pertains to what's going on in the postsynaptic cell. How can something that belongs to our postsynaptic cell discover the value of some variable in some other section that belongs to a different cell? Okay, well, one way to do that is with pointers. And the way we do that is we link some postsynaptic variable to a presynaptic variable with a pointer. And this means that our synaptic mechanism needs to have a neuron block that declares a pointer variable. In this case, I'm saying we have a point process, which is a good representation of a synapse. Most synapses are clusters of ion channels. Most postsynaptic regions are clusters of ion channels that are very small anatomically compared to the length constants in the postsynaptic cell, so they can be treated as point sources of current, and that's why they're represented as point processes. And this particular class of point processes has a pointer called V-pre, which is, of course, a placeholder for that potential in the presynaptic cell. And so how do we couple this pointer to the actual voltage in that presynaptic terminal? Well, in HOC, we would do this by using something called a set pointer statement. And the syntax for set pointer is here, whereas where the mechanism that has the pointer variable that needs the presynaptic value is stated first, and then comma, and then the name of the actual variable that it needs to know the value of. Okay? And that's how it's done in HOKE. And this is kind of an odd syntax, and it's, you know, a little peculiar, but you're going to see it if you look at if you look at any HOKE specified network or other models that involve gap junctions or graded synaptic transmission. In Python, the usage is actually much easier. You just create an instance of your synaptic mechanism class attached to the segment of interest, okay? And once you have that instance, you just use this syntax. This is the syntactic sugar, as Michael Hines likes to call it, for bypassing Python's official inability to deal with pointers, okay? And when Python has imported H from neuron import H, it knows what to do when it runs into this. Okay, Python will know that, okay, at the level of compiled machine language, etc., some kind of a pointer is going to be linked to something else. So this is an assignment statement. On the right-hand side of it is the syntax that returns the location of that is held by that this variable is stored in other words, a pointer to memory where the variable is stored. And we're just saying, okay, that becomes what this has to point to. Very simple syntax, very easy. The thing that needs the pointer gets the pointer by a simple assignment statement. I have to tell you, this is not officially documented in the programmer's reference yet. We need to revise that. It will appear there soon. Okay, fine. So much for graded synaptic transmission. What about spike-triggered synaptic transmission? Let's think about the general case. In the general case, we have a presynaptic neuron with an axon of some length, meaning it's going to have lots and lots of compartments when we discretize it. And it projects to a synapse on a target cell. I haven't included a synaptic thingy attached to this cartoon of a cell, but we'll all understand there's a postsynaptic density there, okay? And our conceptual model is that a spike arises in the presynaptic cell, somewhere in the presynaptic cell's spike trigger zone, propagates all the way down the axon to the presynaptic terminal, and when it gets there, it triggers transmitter release. And we're going to ignore the details of what goes on there, okay, for the sake of implementational simplicity. We're going to ignore that for the moment. And we'll say that once that spike gets there, it perturbs a bag of equations attached to the segment where the synaptic mechanism is connected. So the postsynaptic effect of the presynaptic spike is described by a family of differential equations or kinetic schemes that somehow are perturbed by the fact that the presynaptic spike has happened, okay? And let's think about how we would implement that. We'd have to simulate not just the presynaptic cell up to and including its spike trigger zone, but we'd have to actually calculate assiduously the propagation of the spike all the way down the length of this. So that's a lot of equations. If it was simply Hodgkin-Huxley, it'd be 3 differential equations per compartment. And that's kind of time consuming. Our basic idea then that we just had is represented by this set of boxes here, this little block diagram. So here we have our representation of the cell the presynaptic cell, including propagation from spike initiation zone through the axon to the terminal. At the terminal, we attach a spike detector. When the spike detector discovers that there has been a presynaptic spike and a spike in the presynaptic terminal, it creates an event which is delivered to the postsynaptic mechanism after some synaptic latency on the order of a millisecond or so. Okay? So all of this stuff has got to go on if we were to do the simplest implementation of our basic idea. But wait, what if we can count on our axon faithfully conducting that spike from the spike initiation zone down to the presynaptic terminal every time there is a presynaptic spike with the same latency, with the same conduction latency? If we can count on that, then why do we bother simulating spike propagation through the axon? Why don't we just attach our spike detector straight onto the spike initiation zone of the presynaptic cell, throw away the axon, and then the delay between when there is a spike detected in the presynaptic terminal will be the sum of the conduction latency plus the synaptic latency. So we detect our spike and we wait an equivalent amount of time that it would have taken for the spike to get all the way down the axon plus the synaptic latency before we tweak the postsynaptic region. Okay, that's very efficient. It throws out a whole bunch of differential equations. We don't have to fool with them. Again, the problem with this is if your conceptual model is that there might be there might be axonal propagation delays that are variable, as there might be, say, in patients with multiple sclerosis and partial remyelination, or there might be other reasons why there's intermittent axonal conduction failures, then this becomes not quite what you want, but there's ways to work around that. We could talk about that privately if you're interested in that kind of research. But for most purposes, this is highly efficient and this is highly appropriate, okay, and it'll work just fine. So how do we actually do this? How do we do this? How would we specify this in Python? You've already seen this syntax a bit in some of Robert's slides. You create an instance of the netcon class. And the simplest way to do that is to declare the spike source and the spike and the target mechanism as arguments when you first create that netcon, that network connection class instance. Okay, that's the simplest syntax. If you want, you can also optionally declare other things that are parameters that the netcon has. The netcon has, among its parameters, one is the threshold. That is well, let's talk about what it is actually that we're doing here first. First, we're monitoring the presynaptic membrane potential and in a particular segment, okay, for positive going threshold crossings. Well, of course, that raises the question, well, what is the threshold level? Well, you can specify it as an argument to this if you like, or you can specify it in a separate declaration. I think it's more readable, easier to deal with, it makes your code easier to manage, more obvious if you write them out separately. So you can change the threshold. By default, the threshold is 10 millivolts, okay? So if the presynaptic cell has a depolarization, if the segment that you're looking at, that you're monitoring, has a depolarization that goes above 10 millivolts, that means it thinks the netcon will think a spike has happened, and it's going to put an event into Neuron's event delivery queue, okay, which will be delivered after some delay to the synaptic target. Well, what's the default value for the delay parameter? Well, it's 1 millisecond. It has to be positive if we're going to follow causality. No synaptic terminal can be active before the presynaptic cell spikes. We don't have clairvoyance in these mechanisms. And in fact, if you're dealing with a network model that you want to eventually distribute it across multiple processors, you're going to want that delay to be actually a non-negative value, some value that is actually greater than 0. And what about the weight? Well, the weight is actually an array, and its first element is what classically people that do computational neuroscience have referred to as the weight of a synapse. And that weight is something that specifies how much of an impact a synaptic input has on the postsynaptic cell, okay? And by default, weight is 0. So when you first set up a network connection using a netcon, one of the things you need to do for that to have an effect on its target is to make sure that your weight is greater than 0. Okay. What about the synaptic mechanism? Well, the only requisite for the synaptic mechanism is that it have a net receive block, which the N model code for it has a net receive block, which contains statements that say what to do when an input event arrives. And by default, the weight is interpreted as a peak conductance with units of microsiemens. But the weight could be used for some other purpose. We'll keep it simple here. We're not going to get into obscure stuff. Okay. All right. Yes.
So I'd like to clarify just a little bit about that second syntax on netcon.
Yep.
So in the first case, that source, you could think of that source as being like what we'll call an artificial spiking cell, so like an integrated fire thing or a netstem or anything like that.
Well, we haven't introduced those yet.
I know, but that's the only case where the first case applies. The second syntax where we have a pointer, if we're using a pointer, then with one subtle exception that is so rare that it's not worth mentioning, if we're using a pointer, then you must specify the section that's associated. The section is not optional in that case.
Okay, that's true. This is true in Python. Yes.
And the other thing is, the other little gotcha about this is if you specify, so the pointer and the target, you can either specify the pointer, the target, and the section, or the pointer, the target, and threshold delay weight in section. You cannot specify, like all three of those, if you specify any of those three, you have to specify all three.
Okay. All right. Well, that's an important caveat.
But that's the way it is.
Yeah, that's an important caveat. Always refer to the programmer's reference if you have any doubt. Okay. And actually, there are some there's some example source code that's available that's used in Neuron's development that might be useful because it has potential tutelary value. We should at some point refer to that and point them to it. That exemplifies a lot of features. Anyway, good points. I will revise this slide. Next. Okay, so let's think about what we've got now. What we have now is we have a way of specifying connections between cells, between pre- and postsynaptic cells, that not only can be highly efficient because we don't have to simulate the conduction down the whole length of the axon, but also if we have a presynaptic spike source and we have fan out from our presynaptic cell, there only needs to be one spike detector. You just attach that one spike detector to the location in the cell where the spike initiates. And if you have this presynaptic cell projecting to multiple targets, that's all you're going to have. Neuron will automatically only make that one spike detector, and what will happen, each of these different paths can have its own delay. You'll still create a new netcon for every projection from the presynaptic cell to each target, but internally, Neuron is only going to create that one spike detector that all the netcons are going to share. okay? And the delays can be different, and the weights associated with these different netcons can all be different, and the target mechanisms can be different, and they can be located on different parts of the same cell or on different cells. So fan-out divergence is highly efficient. What about convergence? Well, as long as your synaptic mechanism is described by a set of linear differential equations, then multiple netcons can share that's a single instance of that mechanism. Okay, because superposition will hold. In other words, if you know that there's a particular part of the cell where there's several instances of a particular synaptic class, let's say a GABA A synaptic mechanism, and they're all attached to, say, well, in this case, might be projections from basket cells to the cell body. There might be 50 GABA A synapses attaching to a cell body, okay, of a pyramidal cell or some other cell. Well, each of those synapses can be represented by a single synaptic mechanism because they're all going to have the same reversal potential. The local chloride potential is not going to be different from one to another. And they're all going to have pretty much identical dynamics. That is, ligand-gated channel opening for and closing for a GABAergic, GABA A-type synapse doesn't really vary from, we don't have experimental evidence that it does, from one GABAergic synapse to another GABAergic synapse, as long as they're all GABA A, or if they were all GABA B, they would all have the same kind of dynamics. So if you have multiple synaptic inputs into an electrically compact region, you can represent all of those synapses with a single instance of the synaptic mechanism, and they can all be driven, that one mechanism can be driven by spike streams from each of the different presynaptic cells. So here's a netcon from cell 0, which has its own spike initiation zone and has a spike detector that monitors it and conveys events with a particular delay to our synaptic mechanism, our basket cell mechanism, our basket cell GABA-A-ergic synaptic input to the soma. And then here's another cell, cell 1, with its own spike initiation zone being monitored by a different spike detector and conveying events to our single instance of a GABA-A-ergic synaptic mechanism attached to the soma with its own delay. And so that's tremendously efficient because you only need one bag of equations to represent all those synaptic mechanisms. Okay? All right. Well, let's take a look at the insides of at the guts of one of these synaptic mechanisms that responds to events. Here's an example, a synaptic mechanism whose conductance has a very fast rise and a mono-exponential decay. And we call this an exp-syn because it has a single time constant that describes its dynamics. What do I mean by that? It has a conductance G, a state variable called G, whose conductance is governed by this first order differential equation, an equation that specifies that G will decay, if G is non-zero, it will decay mono-exponentially towards 0 with a time constant of tau. Okay, so you'll see it has a range variable tau, which means every instance of this could have a different time constant. It has a range variable E, which is the reversal potential of this synaptic mechanism, and the fact that it's range variable means the reversal potential can be different for every instance. And it has a range variable I, which is the current actually generated by an instance of this mechanism, and that's a range variable so that every instance of it can generate a different current. And the current that it generates is non-specific so that it is not going to affect any of the ionic concentrations that we might be keeping track of. Okay, so this is a very simple mechanism, and what it'll do is it's initialized so that its at initiation, its conductance is 0. So this is the conductance you would expect such a synapse to have at time t equals 0 if it hasn't received any inputs for a long time. All right. It has this net receive block that says what happens when an input event arrives. If an input event arrives, and the netcon has a single a vector or a vector which we're only using the first element of for this. Its element, that first value of that first element, is going to be interpreted as this value W. And what happens is when this mechanism receives an event associated with a particular weight, that weight is going to be added to the value of G at the instant that the event arrives. So arrival of an input event causes G to be perturbed by adding the weight associated with the event to G. After which, G will resume its mono-exponential decay towards 0. All well and good, but where are the statements that say what kind of a current that generates? Well, they're in the breakpoint block where they belong. And it says here, solve state method CNEXP. What this means is it takes the differential equations in this derivative block, which describes the mono-exponential decay of G, and at every time step, it calculates a new value for G, and then it uses that value for G in this equation to calculate the value of the synaptic current. And that is the product of the synaptic conductance times the driving force for that synaptic current. Okay, so if E is depolarized compared to V, this will be a negative value, and the current will have a negative value, and it will affect our cell appropriately. It will be like an inward current. It will depolarize our cell. If E has a negative value, like say minus 80 millivolts, then we're going to be producing a positive current effect on the cell, which is going to tend to hyperpolarize the cell. It's hyperpolarizing current. Okay? So that's our simple mono-exponential conductance change synapse driven by events. And those of you who are experimentalists will recognize this as a feeble attempt to represent, say, an AMPA-ergic excitatory synapse, which has typically a very fast rise time for the conductance when the presynaptic terminal is active, and followed by a mono-exponential decay of the synaptic conductance. Okay, and this mechanism will produce appropriate summation of synaptic conductance and synaptic current, and will have the correct electrical effect on the segment to which it's attached. Are there questions about this so far? Everybody's got this? Okay. All right. Let's go back to this. So here's an example of our XPSYN in work, in being actually used. We have up here a cartoon of a single compartment model cell whose membrane potential we're going to be monitoring and looking at. And we have attached to it a single instance of our XPSYN class. So there's our synaptic mechanism attached to our model cell. And I'm driving this with two converging afferent streams, which in this case is, we're saying that the stream with each of these little hash marks on one of these streams represents the time at which an event occurs, and time is going from left to right here. So this is the earliest event in the red stream, and these are later events in the red stream. We see the blue stream has its first event somewhat later than the first event in the red stream, and then it has 6 events later on. Okay, so time is moving from left to right here. And we see that the first event is an input from the red stream, which has a rather weak weight, so it perturbs G only slightly. And you'll notice there is a slight latency between the spike in that first, in the red stream, and when the synaptic, when the synapse is activated. So that delay between this red hash mark and the start of this transient is the conduction delay and the synaptic delay, okay? We're saying that actually, it's the synaptic delay. We're saying that there's another stream with events marked in blue that delivers events associated with stronger weights to our synaptic target. And when one of those arises, when one of those is delivered, it produces a larger perturbation of G. If we now say we have 3 events on the weaker stream coming in, we see appropriate temporal summation of the synaptic conductances due to these 3 activations from the events on the weak stream. Then we get overlap in time, simultaneous arrival of events on the weak and strong streams, and we get appropriate summation of synaptic conductances. Just as if we'd had 2 instances of this side by side driven by separate streams, only we're able to do that with a single instance because this mechanism is linear. Finally, the last 3 events that arrive are delivered only by the stream that has the strong weight, and we see the transients, conductance transients produced by those. And we see the appropriate membrane potential changes with appropriate temporal summation of membrane potential, which is always, of course, sublinear in a passive model. And we get all that with that very simple synaptic mechanism that we defined on the previous page. Okay, so now we've looked at the inner details of the operation of this XPSIN mechanism driven by 2 converging afferent streams. What else can happen? What else can we do? We can implement with the netcon, with the net receive block, we can implement synaptic plasticity mechanisms. Here's an example of synaptic plasticity mechanism in which we can get paired pulse potentiation. The conceptual model is that at rest, a single activation of an instance of this particular synaptic mechanism produces some response, okay? So a naive synapse, the synapse that's been resting for a long time, hit with a single presynaptic spike, arrival of a single input event, produces a response of 1e to the minus third microsiemens peak conductance, which then decays like so. And you'll notice this rise time is not immediate. So this is a bi-exponential time course. So automatically we know that the synaptic conductance itself, the time course of the conductance, is described by 2 ordinary differential equations. Now, if we're really clever and we do a paired pulse experiment where we apply first a conditioning pulse and then a test pulse after some delay, we notice that we get some potentiation. If we wait a very long time, the amount of potentiation we get, the amount of increase this is the conditioned response, this is the naive response. We'll notice the conditioned response is a little bit bigger, big enough to notice that it's bigger, maybe 20-30% bigger here. But if we move the timing of the test pulse earlier and earlier and earlier and earlier, we see we're getting more and more potentiation. as we make the interval between the conditioning and the test pulse shorter, we're getting more potentiation. And we'll notice it's got this interesting curvature to it, and it reaches a maximum. There's a certain point at which we have maximum potentiation. And then if we go to shorter latencies between the conditioning and test pulse, we don't get quite as big a response. So this is potentiation that takes a while to develop, follows its own time course, reaches a maximum, and then decays away with time. So this is as if the arrival of a single event triggers some reaction in the postsynaptic terminal, in the postsynaptic cell, that makes the cell more responsive to the next input. Or maybe this is a situation in which all the action is actually going on in the presynaptic terminal. Maybe what's happening is we're looking at the accumulation. This is the effect, could be the effect of accumulation of calcium in the presynaptic terminal. Okay, so that there's a lot of residual calcium that if the second event arrives here, so we get more transmitter release. That could be what's going on. All right, but either way, we're getting a lot of complexity. This envelope clearly looks like it takes two differential equations, this envelope of potentiation, and this envelope of the unitary waveform clearly takes at least two differential equations. That sounds awfully complicated. What kind of code is actually required to do that? Well, let's take a look at the stuff we're familiar with. We'll look at our breakpoint block, and we see that the time course of conductance is calculated as the difference between two state variables. And each of these state variables is governed by a differential equation that has, each of these differential equations has a different time constant. So that's where we get our bi-exponential time course of our unitary response, okay? And of our test responses as well, from the difference between the solutions to these two ordinary differential equations. Okay, so far so good, and we see the usual formula for calculating the current as a product of conductance times driving force. Now, where do we get this potentiation from? Where does that come from? Where are the ordinary differential equations that specify that? Well, they're in here in the net receive block, but in the form of their analytical solutions. So what we have is we have a couple of potentiation variables, G1 and G2. And when the cell is in resting state, when the synapse is first initialized, G1 and G2 are initialized to 0. Okay, and T0 becomes the time of well, at the beginning of the simulation. Now, what happens here when an event arrives? When an event arrives, what happens is the values of G1 and G2 are updated from whatever they were previously by multiplying by a term that looks interesting. This is a mono-exponential decay of G1 over the interval between T0 and the current time T. And the time constant for this decay is G tau 1. Likewise, this is the mono-exponential decay of the variable G2 from whatever it was at time T0 following its own time constant G tau 2. When the event arrives, G1 and G2 are both perturbed by adding a value which is a constant, and the product of these two constants says something about how much potentiation we're getting, and this scale factor allows us to have a nice relationship between the G inc and the maximum degree of potentiation. Okay, So if the maximum potentiation is threefold, G inc would be 3, and G factor is a scale factor that is applied so that this works out correctly when we subtract G2 or G1 from G2. T0, the time at which the synapse was most recently activated, is then updated, and then the effective weight of the synapse is calculated as the product of the weight associated with the netcon and 1 plus G2 minus G1. Well, G2 minus G1 gives us a function that starts at 0, goes up to some maximum, and comes back down to 0. Okay? Because they're both initialized to the same value and they're both perturbed by the same amount. But we want the synapse to have a non-zero response when it's naive, so that's why there's a 1 there. Okay? This is additive potentiation, not multiplicative potentiation. That's why we're adding this potentiation waveform, by exponential envelope, if you like, to 1. Okay? G is then perturbed by that product of the netcon's weight and the potentiation term, the net potentiation term. And then A and B are also perturbed by the product of weight and some factor, which is a scale factor that ensures that if weight is 0.001, that a naive synapse will produce a peak conductance of 0.001 microsiemens. This all sounds very complicated when you first look at it. It's actually very simple. You just have to think it through, scratch out some figures on paper, whatever, you'll eventually get it, okay? But this is a lot of dynamics to have, and you'll notice that we're still actually only solving 2 differential equations. These are analytical solutions to differential equations, and they are evaluated as algebraic functions, and they take almost no time. They increase the computational burden of this synaptic mechanism very little. So you get a lot of, you can have a lot of dynamic complexity with practically no overhead. All right. So we've now looked at an example of what can be done with a biophysical model, a model of a biophysical synapse. And we realize that it's possible to achieve something very interesting here. You'll notice that we can do so much computation if we have differential equations, if we have some process that's described by analytically solvable differential equations. And this process only needs to be updated every time there's a new input event. Maybe we can do something like make an artificial spiking cell, because artificial spiking cells are often described in terms of analytically solvable differential equations. And so NEURON has several built-in classes of artificial spiking cells, and some of them are integrate and fire cells, which impose very little computational burden, essentially none, because they're described entirely by algebraic equations that only have to be evaluated when a new event arrives. And the ability to specify such an artificial spiking cell in such a way has one prerequisite. All the state variables of the cell must be analytically computable once you have a new initial condition. And what's the new initial condition? The new initial condition is what happens when the new input event arrives, okay? And this is orders of magnitude faster than numerical integration because it doesn't involve anything that has to be done with matrix inversion. It's simply it's faster even than Euler's method for numerical integration. And the runtime of a simulation that involves event-driven cells is if you have no other kinds of cell types in there, it's proportional just to the number of received events, because that's the only time these cells have to be updated. It's independent of the number of cells or the number of connections or the problem time. And let's see how that works. Oh, it also raises the possibility we can make networks that include both biophysical and artificial spiking cells. Let's see how this works. Let's consider the simplest integrate and fire cell, the classical leaky integrate and fire. Here we have a cartoon of what's going on inside such a cell. It has a state variable M. We can call it the membrane state, okay? It's not membrane potential, but it's roughly analogous to membrane potential. Initially, M has a value of 0. And it stays 0 forever unless it receives an input. When it receives an input, M is perturbed instantaneously by a value equal to the weight associated with that input. So in this case, the blue input stream is associated with weak weights, and the red stream is associated with strong weights. So every time we see a blue hash mark here, we get a small jump of the value of M. Every time we get an event on the red stream, we get a big jump of M, okay? And in this case, the weights are constant, so every time there's an input on the red stream, we get the same vertical jump of M. Followed by a every last one of these perturbations is followed by a mono-exponential decay of M towards 0. If M is ever perturbed above 1, then the cell, quote, spikes, generates an output event, and its membrane state variable is returned to 0. So here we have an event arrive which is strong, and at the point where M is big enough, there's enough residual M left over from our previous event that this event makes M jump above 1, and which it's reset to 0, and we get an output event, which can be then delivered to targets via netcons. The input events are delivered by netcons that can come from other leaky integrate and fire artificial spiking cells, or they can be netcons that are monitoring, say, membrane potential in a biophysical model cell. It doesn't matter to the leaky integrate and fire model where its events are coming from. All that matters is that it gets an event at a particular time and what is the weight associated with that event. So you'll see again here, you can see the operation of this thing as it receives more and more events and it generates the occasional output. Okay. Now I've assiduously included the mono-exponential decays between arrivals of input events, but if you think about this for a moment, this is only a cosmetic thing, these mono-exponential decays. NEURON actually doesn't have to calculate those details. How does the calculation actually work? The calculation only has to work every time an event arrives. You never have to update the value of M again until a new event arrives, at which point you see, well, how big is M based upon when it last received an input and what the value of M was right after that input. So that is computation only when a new event arrives. So let's take a look at that. Here's our declaration in the NEURON block, artificial cell in fire, which means it's a new cell class, and it's an artificial cell, which means it's not going to have membrane potential, it's not going to generate currents, it's not going to have segments, it's not going to have sections. The only way to communicate with this thing is to send it events, and the only way it can communicate with the outside world is to send events to the outside world. Okay, and it has two range variables associated with it. One is tau, one is M. M so that each instance can have its own membrane state. Tau because you might want some instances of this to have a longer time constant or a shorter time constant. Okay, so let's see initialization. At initialization, the membrane state is set to 0. and the time of the most recent synaptic input is set to 0 as well. And let's look at the net received block, which is called only when an input event arrives. An input event arrives with a weight, associated with a weight W at some time t. What happens? M is updated from what it had been the last time the cell received an event by taking that previous value of M and multiplying it by the exponential decay. How much is the exponential decay? It's e to the minus t minus t0 divided by tau. This is the current time, this is the previous time. The bigger this value is, the longer time has elapsed between its previous event and now, the more decay M undergoes and the smaller this value will become. This value of M updated will become. Then the time of the most recent synaptic input is updated. And then the membrane state is updated by adding the weight associated with the input. Okay, so just like in the presynaptic, in this figure previously, we saw here an input perturbed M up. Then a new event arrives at this time. The first thing we do is we calculate how big is M given a time constant of decay and the interval from the previous input. So that interval is this much, and so we get that much decay. And then we add the weight associated with our new input event. That's exactly what's going on here. Pretty simple, pretty simple. And then the big decision, did the cell spike? Well, we check to see if M is greater than 1. If M is greater than 1, we send an event, we launch an event, which is going to be picked up by all the netcons that are monitoring this instance of the IntFire class, and we reset M to 0. That's all the code. Well, there's some declarations I left out, but this is all the computation that goes on. This is almost free. Okay? Very simple. Okay? I'm not going to go through the other kinds of artificial spiking cells that NEURON has. I'll just recapitulate. In NEURON, it's called, what we just talked about is called IntFire 1 because its dynamics are specified completely by a single time constant. You'll see it also has a refractory parameter, which means once it fires a spike, it will be unresponsive to any further inputs that arise during the next 5 milliseconds or whatever the value of refrac is. Okay? And as you see, if you have an IntFire 1 and you create an instance of it, it will appear with these values in if you're looking at it with a point process manager. Okay. And here's what happens when one of these is driven by a single event with a weight of 0.5 at time 20 milliseconds. Well, actually, there's a latency of 1 millisecond. So what happens is M jumps up at time t equals 21 milliseconds up to 0.5, and then this decays mono-exponentially towards 0. There's an IntFire 2 class, which is a bit more complicated. It has 2 time constants. One is, it has, of course, a membrane time constant, okay, but it also has a synaptic current time constant. And the synaptic current time constant is longer, has to be longer than the membrane time constant. And the idea here is that every time there is an input event, it perturbs the synaptic current. And the synaptic current can start from a non-zero value. So in this case, it's starting with a value of 0.5, the synaptic current is. And at t equals 0, it starts with a value of 0.5. And then when we get an input event, the current jumps up and then decays away. And what we see is the membrane state follows this trajectory. Okay, this is more complicated. If you have a very large input event arrive, what you can do is this thing will fire at least one spike. Since the synaptic current may persist, isn't reset to 0 after a spike firing, if you hit it with a very big input weight, it'll produce a train of spikes that that accelerates and decelerates. Okay. All right. So what about Infire 4? Infire 4 is more. You can set IB to a value above 1, in which case the cell will fire tonically, and then you can inhibit it with weights that are negative, or you can excite it with make it fire faster with weights that are positive. Okay. Infire 4 pretends to be an Infire cell that actually has 2 synaptic currents. One of them is a mono-exponentially decaying excitatory current, which drives M in a positive direction, and it has its own time course, this excitatory current does. So you'll see here it has a tau E, which is, in this case, I set it to 5 milliseconds. That's the rate at which it decays. Its inhibitory current has 2 time constants and follows a bi-exponential time course, and it has 2 time constants here. You'll see these need to be longer than tau E. All right, and you'll see this nice time course here if you had a single inhibitory event. And how does it know it's an inhibitory event? If the weight is positive, and Infire 4 interprets that as excitation. If the weight is negative, Infire 4 interprets that as inhibition. And you see the effect of a unitary excitatory event or a unitary inhibitory event on this model cell. This has more interesting dynamics, more complicated than Infire 2 or Infire 1, and it approximates a single compartment model cell. Are there questions? Everybody's following all of this. Marvelous. Maybe you read the book, I don't know. Okay, so the nice thing about these biophysical model cells, and you can also define other classes yourself, and there are several of them. Now you'll see examples in ModelDB. And you can intermix these with biophysical model cells. You can use these to create a synaptic milieu in which a biophysical model cell is embedded. So you can get these things to create interesting patterns of spikes. There's also something called a net stim, which generates one or more spikes at user specified start time, number of spikes, interspike interval, and degree of randomness, by which I mean the fraction of the interspike interval, which is governed by a negative exponential distribution or Poisson distribution. Those are all built in. And you can intermix these with biophysical model cells. Okay. And you can redefine, you can create an instance of an Infire 1 and give it some other name. You could create an entire class of cells that are based upon Infire 1 and that have a particular set of dynamics. You might want to have fast ampergic and slow ampergic excitation of different kinds of Infire 1s, for example. Okay. So to recapitulate here, defining types of biophysical model cells these are going to be encapsulated in a class. Either you've exported a Hoek class definition from the cell builder or the network builder, or you've written your own in Python. A short excerpt. Refer back to Robert's excellent examples and slides. And when it comes time to creating them, you're going to create them. You're going to create a list. Very straightforward. And here we now, at this point, have 1,000 instances of the cell class, okay, uppercase cell class. All right. So what I'd like you to do for homework, I hope everything was clear so far. I don't see any questions so far. Is there anything on Slack? I haven't been watching Slack. I presume Robert has.
There was one question you can take a look at to see if you want to expand on it, but it had to do with, I want to say, slide 5 and how NEURON chooses which netcon monitoring wins.
Which netcon monitoring wins? I'm not sure I understand the question, but I'll have to look at that. All right, let me see. Where is my Slack? Come on, Firefox.
So imagine somebody creates a netcon monitoring a certain membrane potential, and it has a threshold of 10 millivolts, and another one at the same location has a threshold of 0 millivolts. You're going to scroll up a little bit more. Other up. There you go.
Which spike detector will be chosen?
So for example,
Well, go ahead. Did you already answer this or not? Okay.
Well,
okay. Well, if it's not NEURON's choice. It's more your choice as to how you're writing your code. Yeah, it's what you're pointing to.
but I guess the way that I interpreted that, you can create a netcon that's 2 netcons that are monitoring the same location, the same pointer. And if you do, only one threshold will actually be applied.
Yeah, well, that would be the first one that you created. Will be the one that gets applied. I mean, once you've created that first netcon, that threshold is the threshold for all others that you attach to that location.
Strictly speaking, is it the location or is it the pair of the location and the variable? So for example, one of the things that I use is I use netcons to monitor calcium crossing a threshold.
Oh, well, it's the variable, of course. You can only monitor that once, if you're monitoring voltage, that's the one that, your netcon statement says, when you create a netcon, you're saying what variable you're monitoring. If you're monitoring V, then your everything that monitors V is going to be using the same threshold. And any one of the netcons that monitors V at that location can be used to change that threshold, and it will affect all of them that are monitoring V at that location.
So then is it last one wins?
Any of them. You can, let's say you created 3. Let's say you created netcon 0, 1, and 2. And when you created netcon 1, you set netcon 0. When you created netcon 0, you set its threshold to be 10. Well, suppose later on in your code, you have a statement that says netcon 1 threshold equals -5. Well, they're all going to use the same. You've just changed the threshold for that spike detector, and every other netcon that's monitoring V at that location is going to be using that same threshold because they all refer to the same spike detector. Okay. Now, here's a trick for you. It's a little simple trick you can use. You can create a dummy NModel file, which has a range variable called my V or something like that. And it can have a breakpoint block in which you say my V equals V. So what is stored in my V is the value, the current value of V at that location. And I believe that would allow you, I think you could then monitor that variable. If it's say, let's see, it could be I think it would be a density mechanism you'd want to use for that. Okay, I have to try that and see if that would work. But my idea, my suggestion would be to create a dummy density mechanism that simply copies the value of membrane potential to its own range variable, and then which has some name that you like, and then you can monitor that range variable. Okay, so you can then have multiple different thresholds for detecting a spike, and all of them watching membrane potential. But you know, when would it actually make sense to do that? At a given presynaptic terminal, you're really only going to have one presynaptic mechanism. It's going to be a calcium-dependent mechanism. It's going to release transmitter. I mean, if you're doing mechanistic modeling, you're thinking ultimately, you really forget about V, you're talking about calcium. In a presynaptic bouton, the calcium is the calcium concentration at some point in the bouton. VecStim, yes, specific spike times, yes, good. So it's not a situation that's going to arise. If you have a situation that needs that to be done, you know, come up with a biologically meaningful circumstance, and we'd be glad to address it. But I don't think it's a real problem. If you have, again, you know, has anybody found such a synaptic presynaptic terminal in the world yet? Is it in the literature anywhere? I don't think so. Okay, are there any? Okay, so let's go on to the homework. Here's what I'd like you to do. It's pretty straightforward. I'd like you to make a single section model cell called soma. I'd want you to have these parameters shown in this slide. Very simple, 100 square micron surface area. NSEG is 1, and it's got passive channels. Okay? And the membrane time constant, of course, will be 20 milliseconds. What I want you to do is to attach an XPSIN to it that has these parameters: 3 millisecond time constant, reversal, potential of 0 millivolts. Okay? And I want you to drive that with events from a netstim, okay, that has these parameters, and set the netcons delay to 1 millisecond. Now, what is this? Okay, I left something out on this slide. Let's go. Okay, so what are you going to do? You're going to then you're going to run a simulation for 100 milliseconds, and I want you to adjust the netcons weight to get a 1 millivolt EPSP at the middle of the soma. Just two significant figures for this, okay? All right. I didn't tell you what value to make membrane potential. I'm just saying let it be a resting potential of minus 65 millivolts. Okay. I should revise this slide accordingly. Okay. Now this next question is impossible to answer unless you put a mechanism in there that can make a spike. So what I want you to do is to remove the pass and put in Hodgkin-Huxley. So after you've figured out how big the netcon's weight has to be to get you a 1 millivolt EPSP. For the passive cell, I want you to modify your code for that cell so that it has Hodgkin-Huxley, full-blown ordinary Hodgkin-Huxley, and figure out what is the minimum positive weight that will trigger a spike. Okay. Then I want you to reduce weight to a value that produces a millivolt EPSP in the Hodgkin-Huxley model cell. That's not going to be the value you used with the passive model. And I want you to change the net stims interval to 1 millisecond, the number of events to 1e to the 9, and the net stims noise to 1. What this means is that the net stim is going to be generating events that follow a negative exponential distribution. That is, the interspike interval is going to follow a negative exponential distribution, and the mean interspike interval is going to be 1 millisecond. Okay? And I'd like you to run 100 simulations with that model that include 1,000 milliseconds of synaptic input, and I want you to record the number of spikes you get per run. And I want you to generate a histogram that shows the number of spikes per run with a histogram bin width of 1 spike, of course. Okay? So modulo my errors in this, omitting some details from this slide, that will be the homework assignment. I will revise this PDF and make sure that this becomes uploaded with the correct, fully correct parameters for the exercise. Okay, I think you're ready to do such a thing. And I think that's all I have to say. And now, do we need a break? Are there questions? We need a break? What?
Well, so this is interesting. So we have about half an hour left. Is it worth it to start on the parallel stuff, or should we not?
It's a lot of material. I don't know. I think maybe we should take a break and maybe regroup. What do you think is going to be needed to do the parallel and to give it good and to give it a good exposure? I think it takes at least an hour to do that, right? Don't you?
Yeah, I agree. So I'm kind of disinclined to start it at this point.
Yeah. Well, we got slowed down a little bit with the questions and answers to begin with, and it takes a while to go through some of the concepts of the various integrate and fire and plasticity, etc.
The only thing that I would suggest, if you wanted to say, I don't know if you even have this ready, but if you wanted to say something about what was it, numerical methods, might be relatively fast and relatively not something that's not going to be traumatic.
I might have something. Let me just take a look here. Hold on a second. Let me stop sharing for the moment.
All right, so please stand by. Said I also didn't mean to put you on the spot. I was just trying to.
Right. Well, I have something that I think will do the job. It's fairly straightforward. Get rid of that. And let me share my screen. Okay. All right. As you can see, I've only got 10 slides here, so how difficult can it be to breeze through? Well, the first and most important point is something that's not even on any of these slides, and that is one of the whole points of NEURON is to make it easy for you to use robust numerical methods without having to become an expert in numerical computation yourself. All right. And the concepts that we're going to address are things that I think you've come up against previously elsewhere in different contexts, but I think it'll be in these slides, we'll see how it's pertinent to neuroscience. Good judgment is ultimately the most important part of numerical modeling. Remember that the point of computation is insight, not numbers. Who said that? Who's the applied mathematician, engineer? Who said that? Do you see a hand? Okay, well, I'm open to hearing from you, anybody who discovers who said that. All right, so let's take a look at our situation inside a discretized cell. Remember that what we've done is we've escaped the difficulty of dealing with partial differential equations by discretizing space and time. Again, time to our perception at the scale we're working at seems continuous, and so does space. And what we're doing in our digital computer, though, is we're not solving for every instant in time, infinitely finely ground, nor are we solving for the values of variables at every location in space, down to the level of subatomic particles. What we're doing is we're trying to capture the important variation of variables in space. And we do that, that eliminates a lot of computational overhead. So what we try to do is we try to pick points in space and time that are close enough intervals in space and time that are closely enough spaced to each other that we can capture important departures from linearity, okay? Important curvatures, sudden transients, jumps or transitions of variables, things like that. All right. And so, hence, instead of dealing with continuous cables, which vex us with the cable equation, which is a partial differential equation, we chop cables into pieces called segments, and conceptually, and we solve for our important state variables at the centers of these segments, at these nodes. Why the centers of segments? Because our discretization scheme, because our integration scheme, our discretization scheme uses the second order spatial derivative, and that means that it's second order accurate. We're using second order spatial difference method, which means that solutions will be second order precise at these nodes, internal nodes, and that we can do linear interpolation between adjacent nodes, say for membrane potential. All right. So here we have, once we've done our discretization, we can think of the membrane properties in each compartment as being lumped into a conductance, a discrete conductance, and a black box here, or a gray box that contains all of the ohmic stuff, which are the various ion channels. And in the case of, say, active transport or other electrogenic transport mechanisms, maybe some current sources as well. And these compartments, these elements separate the inside of the axon or the inside of the neurite from the extracellular space, and the adjacent intracellular nodes are separated from each other by these resistances, which represent the resistance of the cytoplasm on the path between adjacent nodes. Okay. And if we had, if we had an so-called extracellular mechanism present, we would be adding a second layer of elements with more axial resistances separating. These are the nodes that represent membrane potential at the outside surface of the cell. These nodes are where the membrane potential inside of the cell, or where the potential on the inside of the cell is located. Okay, so the membrane potential is the difference between this potential and this potential. And and then we have the properties of the extracellular space, which is in this case a capacitor in parallel with a resistor. Probably think of that better as being like myelin. Okay, and then this battery element. Okay, so let's go back to our simplest case, which is a model which is so simple that there is just we can represent it as a single compartment, and we have essentially in a passive model it would be resistor in parallel with a capacitor. And if we were to think about the solutions to the equations that describe that, we would have a first order differential equation that has an analytical solution, which is a mono-exponential decay. And the tau is the time constant of the resistor in parallel with the capacitor. And for the time being, I'm just saying that tau is 1. Okay? And this differential equation describes a situation in which the slope at any given point, that is the derivative with respect to the independent variable time at any point, is equal to -1 times our displacement from the x-axis. So the bigger the independent variable is, the faster it decays towards 0. And of course, as we advance in time and decay a little bit, our slope flattens out a bit until we get over to here where our slope is a bit flatter and our decay slows down, and we get a solution that kind of goes like that. You can sort of envision how that would sort of work. All right. Well, now, how might we actually generate a numerical solution for that? Well, if we were to use the simplest first order approach to doing that, we'd use a forward Euler approach. which means we'd start out at a given point in time, and we'd calculate the slope there, and we'd go forward in time for as long as we like until we get to some new point in time and say, okay, that becomes our new solution point. All we've done is follow that initial slope to here. And here we recalculate the slope, and we follow that slope to here, and so on. And you can see how this solution would sort of evolve. This solid line is the analytical solution. This dashed line is the initial line that we follow when we're going from the initial condition to our first solution point, first approximate solution point. Okay, and these little short lines represent the slope at our different numerical solution points. Well, this is what we get with a time step of 0.5, half of the time constant of decay. But what if we go too far in time? If we go too far in time, we'll overshoot and we'll get spurious oscillations. Okay, we'll end up with a negative value for the independent variable, and then that gives us a positive slope for our next step, and so we'll oscillate back and forth. But if we go really nuts and go far too far ahead, we'll end up way down here somewhere, and we'll get an oscillation that gets bigger every time we advance to a new step. So forward Euler is numerically unstable. Okay, there's a problem with it if we take too big a time step. So we have to take a time step. If we want to avoid the spurious oscillations, we have to take an advance over a time step no longer than our membrane time constant here for our simple model. Okay, and if we want to keep our simulation reasonably accurate, we have to take shorter steps than that even. Well, that's all well and good, except that when it comes time to discretizing cables, when we no longer have an isopotential model, a single compartment model, we find that if we chop our cable into pieces that are short enough to get reasonable spatial resolution of our solutions and capture the important curvatures of our solution in space, we find that this resistance between adjacent internal nodes can be very small compared to the membrane resistance. And that introduces a new time constant, which is very short compared to the membrane time constant. The membrane time constant is 1 here. It's the product of this resistor and this capacitor. And if all these nodes were initialized to the same potential, and then at t equals 0, were released from whatever was holding them at the same potential, let's say 1 millivolt, they would all collapse towards 0 very nicely, and things would be fine. But what if there's a little imbalance, a little round-off error between this V1 and V2? Well, if we take too long a time step, we're going to have a growing error between V1 and V2 that will oscillate and explode. And how big does that have to be? Well, in this case, we have a situation where we have a 1/20th of an ohm here, and we have a couple of capacitors in series that have a time that are 1 microfarad each, and our time constant would be on the order of 1/40th of a second, or to say, well, 1/40th of a millisecond if we're properly structuring this. So this is going to be a problem. We're going to have a little difficulty. We're going to have some serious instabilities. We have to be very careful about this and use a much shorter time step, because if there's ever a difference emerges between these two, our time step now has to be shorter than the equivalent time constant of these two capacitors in series in parallel with that 1/20th of a unit of resistance. So we see here, if we initialize, say, our two capacitors, one to 0 millivolts, the other one to 2 millivolts, and we go forward in time, and we calculate the numerical solution analytically, we would have a nice, smooth collapse toward each other of these voltages, and then there would be a mono-exponential decay with a time constant of 1. But because this is such a small resistance, the first thing that happens is the 2 and the 1 collapse toward each other very quickly, and if we want to capture that time course, we have to have very fine time steps. And so that's why we have to use these very fine time steps initially. But then when the two voltages are very nearly equal, and it looks like things have settled into a slow settling regime, let's see what happens. Can we take a shortcut? Can we make our simulation advance a little bit more quickly by changing dt to 0.2? Well, it looks like we can up to a point, but then we find that what actually has happened is, since there is still a slight, at this point, there's still a slight difference between these two voltages. If we were to magnify these traces, we would find that we were getting growing oscillations at every new advance in time until the solution blows up. So forward Euler is really not stable for us, really not a good thing to use to deal with discretized cable equation, because in our discretized cable equation, our longitudinal equilibration of charge throughout the cell is much faster than the decay of membrane potential toward 0, and we are stuck having to do a lot of empty calculations just to make these two voltages collapse towards 0 slowly, because that's what they will do if we do it right. They will collapse towards 0 slowly, following this nice smooth line, and we're going to have to grind excessively fine to discover that. So this is why NEURON doesn't use forward Euler. Forward Euler might be okay, say, in a model that involves nothing but single compartment model cells, but it's not going to be very useful in a model that has cells with significant electrical extent. Well, what about backward Euler? In the backward Euler method, what you're doing is you are looking for, if you're starting at a particular point in time, you are looking along a curve that of loci such that the slope at each of these loci points backwards to where you started from. Okay? In other words, instead of calculating the next value at the next time based on the current value at the current time, what we're looking at is we're looking for a next time at which the slope will point back to us. So if we go to 0.75 milliseconds as our first advance in time, how far up or down the y-axis do we have to go so that the slope at that point points back to here? That's what we're doing. And calculating that value of y involves a little bit of manipulation. Okay? Then solving this equation is what it requires. And when you have a whole bunch of compartments, what you end up with is a whole bunch of simultaneous algebraic equations that have to be solved through, well, the most direct method is through matrix inversion. Okay? Essentially matrix inversion. Upper diagonalization and back substitution, if you like. And that takes time. That's computational overhead. But the advantage of it is, even though it's slower than forward Euler, it's always stable. Why is that? Well, because if you look at this, what you'll see is the farther out you go, the slower, the lower the slope is, and you're not ever going to overshoot. You're never going to overshoot and get an oscillation. If you go out, say, to 10 milliseconds in one time step, you'll go down the, you go out to 10 milliseconds after one time step, it's way off to the right here on this, I can't even show you, you'll find a value along the y-axis where the slope points back to 1. It'd be way out, say 2 or 3 times further than the right edge of this page, and it's going to be close to, but always above the x-axis. It's never going to overshoot. Nice thing about backward Euler is if you have a linear system of equations, you can find the steady state also in a single solution step. Just choose to go to a point far out in time, and you will automatically get the stable point. Okay, so this is the method that NEURON uses by default, backwards Euler. And here's an example of its robustness. Here's our familiar bugaboo problem where we have these 2 compartments in which the membrane time constant is 1, but you have this other equilibration constant where it's 0.5 times 1/20th is the time constant, and it's a much shorter time constant. And you'll see here, here's the actual analytical solution for our model system. And you'll see that if we take really long time steps, a dt of 0.2, we got a first approximate solution out here, which isn't really super accurate, but at least it's not going to blow up. And we can do another advance of 0.2 of a time unit, and we get a solution which is, again, pretty close to the analytical solution, and you'll notice it is unconditionally stable. So we get the convergence part of V1 converging upon V2. We get that nicely, and with pretty good accuracy, only a small residual error in this approximate solution, just a little bit bigger than the analytical solution is, and you'll find that we get to the portion of this system's dynamics, which is the slow decay, which is pretty close to the analytical solution. So we're handling the phase plane very nicely. We've got the rapid motion portion of our phase plane, approximate, but not getting us into trouble. And then we're now in the slow motion domain of our phase plane, where our traces decay slowly. Those of you who know a little nonlinear dynamics will know what I'm talking about. Furthermore, if we're clever, we could say, hey, look, while things are changing quickly, why don't we use a short time step and get better accuracy? And then when we're close to the equilibration between the 2 voltages, we can switch to a longer integration time step and take fewer steps and grind more efficiently. So yes, this is a more robust approach, and a simple-minded variable time step approach like this would work without blowing up. So that's why NEURON uses the backward Euler as its default method. Another reason why it uses backward Euler is because we're dealing with model systems that are based upon, if we're dealing with mechanistic models of biological systems, we're dealing with systems in which we don't really know the parameters all that well. First of all, it's very hard to know about the actual shapes and sizes of neurites with light microscopy. You're looking at something from the side. You can't tell that it's cylindrical. It might be oval in its cross-section. It might be convex on one side and concave on the other side. In other words, it might have a cross-section that looks like a banana lying on its side. Okay? So you don't know really what the cross-sectional area is of a neurite. Not with light microscopy, you don't. And besides which, there's always blur with line microscopy. So your best diameter measurements, the best they can ever be is on the order of, a half a micron, a quarter of a micron maybe, and that's under superb conditions. And remember, most cells that you can actually record from aren't near the surface of the slice where you can actually see things clearly. They're buried inside layers of injured tissue if you're dealing with tissue slice. And even if you're using sophisticated techniques like confocal scanning laser microscopy or two-photon confocal scanning laser microscopy, there are still limitations to the degree of resolution. So we have a problem with spatial resolution with our imaging. We also have a problem with being able to measure the biophysical parameters of the model. If you look at the literature on the people have been trying to estimate, for example, specific membrane capacitance for a long time. The problem is nobody can tell what the surface area of anything is, and so it's really hard to know what the specific membrane capacitance is. We think it's about 1 microfarad per square centimeter, but there are good experiments that people have done, people with names that you probably should recognize if I mentioned them, but who have done superb work, who have produced convincing experiments that say that under certain circumstances in particular cells, the membrane capacitance might be 0.7 microfarads per square centimeter, or even 0.5, or as big as 1.5, or as big as, in some cases, 2. And we just don't know. And if it comes to channel densities, well, it's very hard to make those recordings. They're noisy. We don't know that we're always recording macroscopic currents, and we don't really know the distribution of channels over the surface of the cell. And with an electrode attached to one point in a cell, it's very hard to know how much of the current you're looking at came from where on the cell and how much of it leaked away through the cell's membrane before it got to you. So we're always dealing with slightly crummy data. 5%, 10% precision would be pretty good if you could get it. So is there a point to try to use more precise methods than a backward Euler, which is first order accurate? Maybe, under certain circumstances. We'll talk about adaptive integration in a future presentation. But again, you got to be reasonable in your application of these techniques. No fifth order runga kutta here. It's first of all, they're not stable enough. And secondly, we don't have sufficient quality data to justify using that kind of precision. And so when somebody publishes a model and they give 12 place specificity, or maybe 20 place, when they print out their parameters in Python and they're getting these enormously long strings of numbers, I take that with a real grain of salt. I mean, we don't know anything biological to that level of precision. And furthermore, how precise is a frog anyway? Any animal, any organ system, any function, any biological function that requires super precision of any particular state variable is not going to be robust. Okay? It's not going to work. An organism that depends on super precise parameter values is not going to function well day to day. Okay, next slide. There are other integration schemes built into NEURON. One is Crank-Nicholson, in which the algorithm is roughly equivalent to taking your time step that you're going to advance over and looking for the point halfway along that time step where the slope is going to point from your starting point to your destination point. And you can do that by doing a half a step of implicit Euler followed by a forward, that is an explicit Euler half step. Okay, that's cheaply implemented. The Crank-Nicholson method gives second order precision in time, and it can be used with a larger DT and yet preserve good accuracy. The Problem is, if the DT is too large, it can have spurious oscillations, but fortunately, they don't explode. They'll always go away with time. They're just unsightly, and you'd never get that published in a scientific journal. It is amenable to simple-minded variable time step approaches, and it converges faster, and you can get your solutions with a little bit less effort than you can with, if you're grinding away with implicit Euler. And you can select Crank-Nicholson with NEURON, but you have to be careful because it doesn't work if you have a system that is too stiff. And what's too stiff? A system is too stiff if the time constants in the system vary by far too much. And what makes time constants go down to very small values? Voltage clamp. If you have a model that involves a voltage clamp, it's not going to be amenable to Crank-Nicholson. You're going to have to get rid of that voltage clamp in your circuit, in your model specification, or you're not going to be able to use the Crank-Nicholson method with it because it will definitely blow up when the voltage clamp does a sudden transition. Okay, it'll blow up even before that because the voltage clamp imposes a very low local resistance and infinitely high or extremely high conductance that that really makes the equations extremely stiff. NEURON also has an adaptive integrator, which is the first one that was included. It was called CVODE. It was a bag of different strategies. Now there's more different strategies in it, but for compatibility with previous nomenclature, we call it CVODE. Even though it's no longer CVODE, it's a bunch of other things. And the nice thing about the adaptive integrator is it automatically adjusts both the time step and the order of integration in order to get you the desired degree of precision. You don't specify a time step, you don't specify an integration, well, you don't specify an order of integration. The integration algorithm chooses those things for you. You say what is the error tolerance you're willing to put up with, and it will automatically adjust the integration as it goes along in time. And if you're careful about choosing these parameters, you'll get a relatively efficient simulation that is relatively high in precision. The utility of this adaptive integrator is to get accurate results. Sometimes it's helpful for systems that have particular kinds of equations. It's often helpful for models that involve certain calcium accumulation or release mechanisms that have peculiar dynamics. Okay, because it will succeed where other methods will fail. You have to be careful about choosing the error tolerance. The sloppier the tolerance, that is, the larger the error that you allow, the faster the integration scheme will operate, but you'll get these spurious oscillations and weird transients. Okay, NEURON has a graphical tool that allows you to deal with that very nicely. We may return to that later on in this course. Now, just one last in closing, I want to mention something about judgment. This slide, the top figure shows a couple of sets of traces. This first cluster of traces are numerical solutions for a single compartment model with Hodgkin-Huxley. Okay, and the stimulus in this for this first set of solutions is big enough to robustly initiate a spike. Okay, it's a relatively large stimulus, 0.15 nanoamps. Always put a 0 in front of the decimal point. Never just put a decimal point. It's very hard for some people to see those decimal points if they have astigmatism. It doesn't hold up well in graphical reproduction in journals to leave out the leading 0. Always put a leading 0 in. Okay. And we generated basically 4 solutions here, and the methods that were used. One of the methods used was the fixed time step, the backwards Euler method, with a time interval of 0.025 milliseconds, 25 microseconds. That's one of them. Then 2 of them were Crank-Nicholson methods, one of them with a time step of 1 microsecond and one with a time step of 25 microseconds. And the 4th one was adaptive integration with an error tolerance of, that is, of 1 e to the minus 2. In other words, every state variable that was being solved was solved so that the local error at every f advance was smaller than 0.01. Okay, so what are our state variables? M, N, and H, and membrane potential. Membrane potential is always pretty big, except when it gets close to 0 millivolts, which is a little odd, but it's generally much larger than 0.01. M, N, and H are generally much larger than 0.1. So this is a fairly stringent error tolerance. Okay, and you'll see that with a strong stimulus, that all of these solutions look pretty similar. The one that's a little bit off is the implicit Euler, that backwards Euler, NEURON's default method, and it's the one that's a little bit slower than the others in terms of this decay phase here. But they're all pretty close. That's good enough. That's good enough for most qualitative insight and most semi-quantitative results. But what happens now if you reduce the stimulus intensity to a value which is just big enough to trigger a spike? Well, this isn't as bad as it could be. It could be slightly smaller, but here the stimulus intensity you'll see is 0.061 nanoamps. That label should be right up next to these or next to this trace here. And you'll see that they all look like all the solutions are pretty close to each other until we get right about here at about 1.5 milliseconds, when these 3 methods start to accelerate, their solution accelerates up into a nice spike. And then the laggard is our old friend, the implicit Euler. So we see that when our system is operating in a regime where it's going to be dwelling close to a threshold for spiking, close to a separatrix, for those of you who are nonlinear dynamicists, you'll see that the implicit Euler method gives you a qualitative result, which is okay, but quantitatively looks very sloppy compared to these other more precise methods. Okay, so this looks like if we were working on a model in which spike timing was important, like let's say we're working in a model that has spike timing dependent plasticity, or let's say we're working in a model of coincidence detection in an auditory system where we want things to happen at the right times. Very important. We would definitely want to use one of these other methods to avoid having this little bit of a problem here, okay? Because that could be quite destructive of a result in a spike timing dependent plasticity exploration or a coincidence detection setting. So you could say, all right, integration method is important under certain circumstances. But what about these examples down here? Again, we're doing the same thing, except I'm only comparing one of these solutions. I'm comparing the adaptive integrator solution with the implicit solution. Excuse me, no, I'm doing the adaptive integrator, period. These are all generated with the adaptive integrator. So we know we're using a highly precise method. This can go up to fourth order or higher numerical integration, and it can use very fine time steps, okay, to achieve high precision. So these solutions are all generated with the adaptive integrator, the gold standard, if you like. And you'll see two solutions here with a large stimulus. One solution is with the standard GNA bar, and the other one is with GNA bar reduced just a tiny little bit compared to the standard Hodgkin-Huxley value. Okay, so, what's the standard GNA bar? Does anybody remember? Okay, GNA bar HH is 0.12. Okay, that's fine. And what happens, oops, excuse me, that shouldn't happen. What happens if we reduce GNA bar by 1% from 0.12 Siemens per square centimeter? Just 1%. 1% reduction of GNA bar. We see that with the big stimulus, the solutions are practically identical, regardless of the fact that one of them is generated with a GNA bar that's 1% smaller. With a stimulus that's close to threshold, we see that with the larger GNA bar, we get a solution that produces a spike that's earlier. With that 1% lower GNA bar, we get a solution that is significantly later. This difference in spike times is pretty comparable to the difference in spike times we saw here. But instead of being caused by a difference in integration methods, it's being caused by uncertainty in a parameter. Well, I can't select that parameter all by itself, can I? Uncertainty in a parameter. You can't name a single channel conductance that's been measured to within 1% of its actual value, and it wouldn't be the same from axon to axon anyway, because of biological variability. Given the slop that affects channel densities and anatomical measurements and practically everything we try to measure, it's you can see that you're going to get problems whenever things are close to a firing threshold, whenever you're operating near a separatrix that separates trajectories between those that go into a spike and those that simply collapse. So the longer your model has a state variable that hangs on the precipice, the more error you're going to get in your simulation result. That's not a consequence of a problem with our integration methods. That's a consequence of our ignorance and our inability to measure parameters to the necessary degree of precision. So there's always going to be errors. Okay, so when you see something like this, which is different between implicit Euler and adaptive integration, and you say, well, implicit Euler is not that good, just realize even the adaptive integrator is subject to errors that you don't even know about, because of errors you don't even know about these biophysical parameters and their values. Just talk to an experimentalist sometime, and make pals with an experimentalist and find out what are the limits to the characterizability of these parameters, and then begin to think new thoughts about how much precision can you expect from a simulation? How much can you rely upon the exact numerical values that you get out of a simulation? A pragmatic approach would be to say that you should be looking at qualitative and at best semi-quantitative results. Okay, don't get hung up on exactness and precision. And by the way, the engineer is a guy by the name of Hammond, Hammond. The purpose of computing is insight, not numbers. All right, that's all I have to say for today, and I will get you a revised PDF for the homework problem later today. Any questions? All right, we'll see you all next Tuesday. Bye-bye.